Hello, everyone. My name is Holger Mistakis, and today, me and my coworker Jake Muldoon will talk to you about chemical similarity, which are similarity scores, our RIFM approach to chemical grouping, and read across. So to begin with, what is Tanimoto score? Well, Tanimoto score is one computational measure of similarity that can compare chemicals encoded into fingerprints, allowing for easy structural similarity comparison between target materials and potential read across analogs. We have a couple example chemicals on the screen here, with our target being isopropyl propanoate. We have two different materials here, isopropyl isobutyrate and dipropyl malonate. Both are esters, just like our target material, and we're trying to see which one would be a better potential read across. And one way we could do that is by looking at structural similarity score, or the Tanimoto score. When we look at the Tanimoto score of isopropyl isobutyrate, we see that it has a 0.84 score, which means it's 84% similar to our target material. Looking at dipropyl malanoate, it only has a Tanimoto score of 0.51, which means that it is only 51% similar to our target, which means that based on structural similarity alone, the isopropyl isobutyrate will be the better material to use. Now, this is a common way to go about looking for read across, but we want to tell you some limitations that this method might have. And to do that, we'll start with an analogy. So you want to sweeten your tea, but you're out of sugar. All you have are salt and honey. Salt looks the same as sugar, but will not sweeten your tea, as I hope you know, while honey looks completely different from sugar, but would sweeten your tea. And this is a good comparison to structural similarity, right? Where salt is very structurally similar to sugar, both white powders, but have completely different use cases, where honey is structurally very different from sugar. So while Tanimoto score can be useful in comparing directly the structural similarity of two materials, there's limitations in its use. Computational measures of similarity can give too much significance to certain parts of a material to increase the similarity score, and too little significance to other parts, which lowers the similarity score. While ideally a target chemical and a read across analog would have a Tanimoto score of 0.8, this is not a hard and fast rule, as we've learned from our experience using these. Lower Tanimoto scores can be appropriate if the read across analog has all the necessary reactivity present in the target chemical. So now I'm going to go through a couple of examples of materials where the Tanimoto scores are a little off, but why we would want to use a lower similarity score compared to the one that has a higher similarity score. So in this first material, we have linalool. Linalool has a couple of unsaturations and a tertiary alcohol present. When comparing to linalool, 2,6-dimethyl-2-heptane-6-ol has a Tanimoto score of 0.93, 93% similar, very, very close. However, Tanimoto score does not always compare reactive features accurately. In this material, we are missing a key vinyl group, which is going to be very reactive in both of these materials, in this material. When we compare it to dihydrolinalool, which has a Tanimoto score of only 0.5, the only difference is the fact that we have a triple bond compared to a double bond in our target material. Tanimoto score treats these two structural features, vinyl versus propalgyl group, as being very different. And that's why the similarity score is so drastically low comparatively. However, the reactivity that you'd expect from a triple bond is not dissimilar from what you'd expect from a double bond. It would just be more reactive, in fact. So therefore, this would be a better read across analog because we'd be capturing some of the reactivity where the material that has a Tanimoto score of 0.93 does not have any of that reactivity present. In our next material, we have osamanol, which is another tertiary alcohol which has a conjugated vinyl and vinylene group. Again, we look at a material here that has a Tanimoto score of 0.8, which is dihydrolinalool. That is a pretty good similarity score. It has a tertiary alcohol and it does have a vinylene group present, but it doesn't have the vinyl group, which is a major reactivity center. Also, it doesn't have any conjugation between groups since it only has one isolated group itself. Ricinyl acetate, which has a Tanimoto score of 0.54, much lower, but it does have conjugated vinyl groups here, which would be even more reactive than what we see in the vinylene vinyl group conjugation in our target material. The biggest difference here is the fact that the read across is an ester, but this is less of a concern since we know esters would undergo ester hydrolysis, forming the tertiary alcohol that we see in our target. So after metabolism, we would still have very similar reactivities, and there's not much concern from the acid moiety that would be formed here. So again, Tanimoto score does not always capture similarity in reactivity, such as conjugated dienes versus an isolated vinylene. While the structure is higher, we're not capturing the reactivity present there, so therefore the lower Tanimoto score would be better. Moving on to our final example, we have 2,6-dimethoxyphenol. If we look at benzene 1,3,5-trimethoxy, it has a Tanimoto score of 0.87, and it makes sense because it has three functional groups that all have heteroatoms, just like our target material does. And our target material does have two methoxy groups and a one alcohol group, and we have three methoxy groups on this material. It seems like it makes sense that this would be a good read across. However, what's not being considered by Tanimoto is the similarity in terms of potential metabolites. Our target material could go under O-demethylation to form two alcohol groups here, which could form a catechol, which are very reactive. Therefore, in this case, just using catechol as a read across, which has a much lower Tanimoto score due to the difference in functional groups and missing one of them entirely, really, right? Is still a better case because that metabolite is the metabolite of concern here. So therefore, using this as read across would be appropriate. So to conclude this section of this, in some cases, higher Tanimoto scores can be misleading and result in inappropriate read across analogs. Additionally, omission of lower Tanimoto scores could exclude appropriate read across analogs. And while structural similarity scores can be misleading, another way to compare materials is through chemical grouping, and which will be the next portion of this talk. So, what is chemical grouping? Well, chemical grouping is the method of grouping chemicals. But how do we group them? We group them via their, structural features or their reactivity or the potential metabolites, various different functionalities there. So let's say we had this group of shapes of different colors. We have squares, circles, stars, and triangles. We could group these in numerous ways. One way is by their shape. So we put all the squares together, all the stars together, all the triangles together, and all the circles together. That's good. But there are other ways we could group this as well, right? We can instead group them by their colors. So which one is the best way to group these? And that's something that we've been looking into for how we can group chemicals, since there are so many different ways you can group them. In the past, RIFM published large group assessments where chemicals were grouped together based on 1 to 2 specific functionalities that were considered the most chemically and toxicologically significant. Some examples are shown on the screen. We had groups of aryl alkyl alcohols, branch chain saturated alcohols, cyclic acetates, or macrocyclic ketones. The groups here could contain as many as 40 different chemicals. Since then, the science has progressed, spurring RIFM to publish individual chemical safety assessments. RIFM realized that the chemicals in these broad categories could have different chemical and toxicological properties from one another. For example, in the shown on the screen from the cyclic acetates, both of these materials were in this one assessment. However, while they are both cyclic acetates, the functionalities of the material with the two double bonds in it would be very different than the reactivity and potential metabolite formers of the material with no double bonds in it. Therefore, in 2012, it was decided it was crucial to perform safety assessments on individual chemicals to address these differing properties. Individual chemical safety assessments also allow for material evaluation using realistic human exposure. So, to assist with these individual chemical safety assessments, a more nuanced grouping method was needed. In an effort to group chemicals scientifically and appropriately, all structural features must be captured. To do this, we create a structural activity group for each chemical in our inventory, which contains all of the structural features of the chemical ordered in increasing specificity. I'd like to turn this over now to Dr. Jake Muldoon to explain the work we have done in creating standardized decision trees to create these structural activity groups for the over 6,000 materials in the RIFM database. Jake, all you.
Thank you, Holger. And as you were talking about the systemic way of us being able to group molecules within the RIFM database, the first approach that we do is we group based on the heteroatom. That is, if there is no heteroatom and it is just a purely hydrocarbon skeleton, or do we have the presence of a heteroatom in the case of whether it be oxygen containing, nitrogen containing, or sulfur containing. If we look inside the red box here for the oxygen-containing molecules, we can even look at them in that case and then go into the next feature. So the first thing we would establish is what heteroatom is present. In this case, in this example, would be oxygen. Next, we look at the key functional groups that would be distinguished. And in this case, if we have multiple functional groups from acids all the way to ethers, we even judge them based on a priority if there were multiple functional groups present. Same thing going on with the heterocycles from epoxides to pyrans. I would like to draw your attention over to the right-hand side to ethers, and we can look at an example in that case. So if we take a look on the right-hand side here for anisole, we see now that we can ask ourselves the next questions for the key structural features of this molecule. And this is where our decisions trees come in. And the questions that we ask come from the institutionalized knowledge that we have here at RIFM. So the first thing we would ask ourselves is this a monoether or a diether? Then we can ask ourselves, is it alkoxy or aryloxy? In this case, we see that there is a ring directly attached to the oxygen heteroatom. Now we see that ring, then we want to know more about its structural features. So do we have one ring or multiple rings, so monocyclic or polycyclic? And then after we've established the size of our ring, we then want to ask ourselves, what about any forms of saturation or unsaturation within the ring itself? So is it aromatic or saturated? So now from there, we are able to establish a little bit more key structural features of this molecule to give it more of an identity or a structural activity group, a chemical characterization. So if we look at the next slide, we can see that we can get this in a top-down approach of decision trees. And by following the decision trees, we can take a molecule and be able to give it a group for it to be in. So again, just as I made mention in the previous slides, if we first take a look, we group based on the heteroatom, oxygen containing. Next, we would distinguish the functional groups. In our example, it was an ether. And then following that, we would then continue on identifying key structural features to give this a very unique structure activity group that would help place this molecule in a grouping or a cluster for us to be able to use it later on in cases such as read across or other forms of predictive toxicology. Now, in this case, just looking at an ether decision tree, we understand that this can be rather expansive, but we want to make it clear that the decision trees take into consideration very comprehensively and robust scientific features for us to be able to make these classifications. And we are now currently working on being able to automate this procedure so one does not have to manually go through these trees, but rather have your molecule and then be able to automatically give you a structure activity group by running it through an automated process of going through these decisions trees for you to make it more user friendly. And with that, I would like to hand it back over to Dr. Moustakis.
Thanks, Jake. So, using all of that information, how do we actually group chemicals and what do our structure activity groups look like? And we can look at a specific example going back to anisole. So we have anisole and we have its structure on the side here. And what we have below is the full structural activity group for anisole. So if we click through, we can see the first thing we need to note is the ether, much like Jake said. So this is then classified by the terms oxygen containing, ethers, monoether, and aryl oxy, which defines everything about the ether here. Continuing on, we have the benzene ring, which is defined by cyclic, monocyclic, and aromatic. then the other side of the ether, which is just straight chain and saturated. And finally, we take the entirety of the molecule and count the carbons to give it a carbon range useful for bioavailability and skin penetration. So here, C6 to C13. The structural activity group can be thought of as an address for a chemical. Much like our address for our current office space is in North America, USA, New Jersey, Bergen County, Mahwah, and then at 112, 1200 MacArthur Boulevard, I apologize. We can then go from very, very broad to very specific to really lead you to exactly where our office is. These structural activity groups work exactly the same way, whereas we go from a very broad category such as oxygen containing all the way down to the specific carbon number, which gives it a location among all other chemicals in the inventory. And I'd like to mention that we have a video on YouTube that is an animation that kind of gives an overview of this process. And we'd love for you to check that out afterwards if you're interested. So how are the structural activity groups used? Like I said, just like the address, the structural activity groups give the chemicals a location among the entire inventory. Chemicals are sorted by their structural activity group so that chemicals with similar structural activity groups are closer together. Furthermore, chemicals with the same structural activity group form what we call a cluster. Here we have anisole and N-butylphenyl ether. Both of these have the exact same structural activity group, which is what I showed previously. If we go through these highlights, light blue showing the definition of the ether being the same between these two, the purple showing the benzene group, again being the same definition, the opposite end of the ether being straight chain and saturated again, and finally, both of these falling into even the same carbon count range. So we recognize that the fragrance chemical space is just one part of the larger chemical world. However, we really believe these principles can be applied to any chemical, just with an expansion of the decision trees that we've already created. Structural activity groups also assist in the read-across selection process. Read-across is a structure activity analysis encompassing various techniques and approaches to solve gaps in toxicity prediction. The concept of chemical similarity is central to the read-across method. By being able to group similar chemicals together or close together in adjacent clusters, we can more quickly find appropriate read-across analogs since we know they contain all the structural features of interest. Read across as a tool can also help us avoid the need to carry out specific tests on every substance for every endpoint. In particular, we think of read across as a very useful and critical non-animal methodology so that we can avoid animal testing. Structural activity groups sort chemicals together, allowing for the easier selection of potential read across analogs. We group read across into different tiers based on the structural activity group. For our target material, should be familiar with this one, it's isopropyl propanoate, right? We saw this earlier. We have a couple different options for read across. A tier 1 read across would have the exact same structural activity group. An example here would be isopropyl pentanoate, where it has all the same functionalities as well as having the same carbon range count. Tier 2 read across are read across that have minor structural differences or minor changes in their structural activity group. Here, isopropyl decanoate is very similar to isopropyl propanoate, except that it has a larger carbon count, which would put it in a different carbon range, meaning one term would be different in those groups, which would mean they're in different clusters, but they'd be very close together overall. Finally, we have tier 3 read across analogs, which have major structural differences between them. Here, the two shown here are isopropyl alcohol and propanoic acid, which are obviously very structurally different from isopropyl propanoate. That's an ester, and these are an alcohol and acid. However, these are the exact metabolites from ester hydrolysis, which means that we would assume the ester to undergo ester hydrolysis and form these. So having data on these make an appropriate read across to our target material. However, because of the structural differences, we classify it as tier 3. Their structural activity groups would be significantly different. So we can go into an example of how our method has refined grouping with these aromatic ethers. All four of the materials shown here, anisole and butylphenyl ether, which we've seen previously, p-methylanisole and methyl 1-naphthyl ether are all aromatic ethers. They are all ethers connected right onto an aromatic system. However, we can make a lot of distinctions between these. We've already noted how anisole and N-butylphenyl ether do have the same functional group. But if we move on to p-methylanisole, we can see that it has the addition of an alkyl substituted group that's captured in our structural activity group through the bolded alkyl substituted and para substituent there, which changes the structural activity group, though minor, um, putting it into a different cluster. Finally, for methyl 1-naphthyl ether, we see that the structural differences are actually pretty high here, and that's reflected through the addition of polycyclic, 6,6 ring, and fused in its structural activity group, as well as diaromatic. All of these are significantly different from the original ones we saw, which would probably make this closer to a tier 3 analog in our grouping scheme. Another example of refined grouping can be found using the fused tricyclic ethers with short chain polyalkyl substituents. All of these are fused ethers, in-ring ethers, with 3 rings all fused together. The first material, for simplicity's sake, will go by its trade name of galaxolide, um, has a benzene ring in it, which the other material, amberfix, does not. We capture these through their structure activity groups, as mentioned here. These are the 2 structural activity groups for each of these 2 materials. And then we could then highlight showing where one of the rings is just noted as aromatic for galaxolide, while for ambofrix, we define it out, saturated alkyl substituted straight chain saturated, just like the other rings that are present there, meaning that these 2 would be in different clusters as well, even though by the title of the name, they could be grouped together, but we would expect different reactivities from a benzene ring versus a completely saturated ring. So here, we can further see how grouping through use of structure activity groups can inform toxicological properties by looking at these examples. These 3 materials, again, I'm going to use their trade names for simplicity, fluoroazone, cyclamen aldehyde, and liliol are all very structurally similar and could fall into these arylyl aldehydes group. However, if we create the structural activity group for these materials, we see that they do have differences to note. Some are straight chain substituted, while some are branched, and their total carbon counts differ. And this is important because these 3 materials have different toxicological profiles in rats for reproductive toxicity. Fluoroazone does not produce any toxic metabolites for rats, and is considered non-reprotoxic. Cyclamen aldehyde does form some amount of toxic metabolites, but in significantly low quantities. Lilial, which I'm sure many of you have heard of, does form toxic metabolites in significant quantities, meaning that it needs to be separate from all the materials. But our grouping does that inherently just as it is. These would not be considered all in the same group, where fluoroazone has a straight chain compared to both cyclamen aldehydes and lilial's branch chain. Furthermore, fluoroazone and cyclamen aldehyde both are in a different carbon count range than lilial itself. Because our grouping was designed with toxicological data in mind, it has the ability to capture that in its structural activity groups, as is shown here. So while the structural activity group is important, it's really only the first step in the process. Structural activity groups only consider the chemistry side of things. We also want to consider the data we have from various toxicological endpoints when we consider the clusters and potential read across. As I mentioned, it is built in to how we've considered, since we are considering structural features that we know have toxicological significance. However, there are still some times where we might see toxicological differences based on endpoint in a cluster, and that's what I'm going to touch on now. So how do we incorporate endpoint specificity into the clusters? Well, let's go back to our original shapes and colors example for simplicity. Let's say for skin sensitization, we realize that stars happen to be skin sensitizers. It's some particular feature of that to separate it out. We can then separate the stars from their original clusters and mark them as a separate cluster specifically for skin sensitization. While the color, for instance, might be the leading feature for, let's say, genotoxicity, we see that difference in skin sensitization and would be marked as a different cluster for them. Continuing with the example, it can be done for any endpoint. Let's say if circles had a reproductive toxicity concern, we could separate those out as well, specifically for that endpoint. So going back to the aryl aldehydes group, we have two other examples here, rhodiol and lilial, which we mentioned previously. Both of these materials have the exact same structural activity group. However, they form they have different tox profiles overall. Rhodiol forms toxic metabolites, but again at a very low quantity, much like cyclamen-aldehyde, whereas lilial again forms toxic metabolites in a quantification that is mm, something that we need to be concerned with. We can highlight these again to show the noteworthy regions and say, these are the features, oxygen-containing aldehydes in light blue, defining the not only aromatic ring, but the substituents there in purple. Again, the branch section substituent for the benzene ring in dark blue, and finally the carbon count all being the same. So, like I mentioned, there are differences in the metabolites that are formed here that have potential for reproductive toxicity in rats. Um, and, there are minor differences in structure here. For instance, rhodial has an isopropyl group compared to the tert-butyl group in lilial. This feature really would probably be no concern for another endpoint such as genotoxicity or skin sensitization, but here that might be the reason why we're seeing such a difference in the toxic metabolite formation in rats. So for that reason, we can separate these two materials for the reproductive toxicity endpoint here. So we would like to note that RIFM is dedicated to the peer review process and making its research available to anyone, free of charge. We have two papers out right now that touch upon much of what was discussed in this talk. They're both completely open access. The first paper is clustering a chemical inventory for safety assessment of fragrance ingredients, identifying reading across analogs to address data gaps. This gives a general overview of how we cluster materials and how we separate them based on their key functionalities and how that allows us to better assess them for read across potential. The second paper is an endpoint-specific framework for read-across analog selection for human health effects, which goes into the details of the differences that we need to consider per each endpoint when finding read-across. Read-across is often thought of as a one-shoe-fits-all sort of thing. Again, really heavily relying on that structural similarity score from Tanimoto. But we would like to propose that, different endpoints have different concerns, reactivity being one for genotoxicity or skin sensitization, for example, while structure and metabolism is maybe more important for things like repeated dose toxicity and developmental and fertility. So this paper discusses those sort of considerations. In addition, the specifics of our decision tree and structural activity group process are currently being compiled into a publication as well. So from this talk, I hope we have showed you how current measures of structural similarity can be flawed and why appropriate chemical grouping is so critical. Through the use of structural activity groups and endpoint specificity, the RIFM approach to grouping is scientifically robust and assists in appropriate read-across selection. The RIFM approach to chemical grouping has been developed over many years, transitioning from large groups based on 1 to 2 functionalities to smaller groups based on structural activity groups. The structural activity groups provide complete information on the functionalities present in a chemical, which allows similar chemicals to be sorted together into clusters. The structural activity groups assist in the read-across selection process by having similar chemicals close together and separated into tiers based on the degree of structural difference. The issues of large grouping can be seen through the examples of the aromatic ethers group and the other groups I've shown as well. The grouping methodology can be further refined when considering endpoint-specific events, creating clusters that are specific to any endpoint, such as for reproductive toxicity with those examples I showed at the end. So, I would like to thank you all for your attention, and we're happy to answer any questions and have further discussions in the breakout room that follows this talk. Thank you again.
Thank you.